So I have some carts here. You guys see my carts? Go, go, little cart. Can you make some observations about what you saw? Okay? Make a nice observation out loud, please.
Can you do it one more time?
I can do it all day. It's very satisfying. Kennedy.
They're like bouncing on each other.
Absolutely. There's obviously some bouncing. Evan.
I don't know if I'm right to say this, but like it's transferring its energy to the other card.
That's actually a great statement. He says, I think that the one car is transferring energy to the other car. That may be true. Okay? How are they bouncing? Like if you look closely or listen closely, are they actually hitting each other?
Yeah.
Are they? Now,
I was just gonna say that the one car that you like initially push stops when it hits.
yeah, did you guys notice that? Like this one coming in, comes to a stop, and the other car moves out. That's a great observation. What else? Oh, by the way, yeah, so they're not actually hitting each other. Listen closely.
Oh, they're magnets.
Yeah.
How are they not hitting each other? Magnets. Totally, right? So, here's a magnet here. Yeah. Okay, now, I can bring this here, watch, it's going to push it without touching. Is that weird? Can magnets do that?
Yeah.
They can, right? What has to be true for magnets to repel each other like that? What?
They're like opposite ends.
Opposites
No.
repel?
Oh, no, I meant, right? They're like the same.
Good. So opposites do what?
Attract.
Attract, right? True for magnets, not true for relationships. Okay? So I have a magnet here. Let me bring it in here. Do you see it move this card?
Yeah.
Without touching? It's cool, isn't it?
So those are two of the same or two different ones?
So magnets have two sides. We call them north and south. Okay. Now, I don't know which one's north and which one's south. Here, yeah.
What is a magnet made of?
Normally they're made of iron. This one's made of something else called neodymium, but normally magnets are made of iron. So I'm going to bring this in here. Whoa! Did you see that? Now I'm going to turn this around, and now it's going to push. So I don't know whether it's north or not. I just know that this end and this end are the same. So what's it going to do? It's going to repel. Now watch, I'm going to turn it around. And now it's going to happen. Is that cool? So, this is going to attract this one. Now I'm going to turn it around again. What's it going to do to this one? So, this side is opposite with this. This side is opposite with this. What does that tell you about this one and this one? They should repel, which they do. Is that cool? Y'all on board with that? Fantastic. So, magnet. So we have some observations. We got this one, the original one comes to a nice stop. This one goes out. We can do the same thing this way. We think some energy might be transferred, right? Can you make an observation about the speed of the car as it exits the collision versus the speed of the car when it comes in? Did you notice anything? Yeah, does it look like they're the same speed?
Yeah.
It totally does, right? So let's diagram this out and see if we can't use our bar chart to get an understanding of this. Does that seem okay? All right, so let me draw the before and after picture. So the before picture looks like this. The after picture looks like this. Okay. So what's in our system?
Car,
You want to call me Andy?
yeah,
Is that cool?
yeah.
How's that? Is that cool? I'm going to do this one for you guys, and then the next couple you guys can kind of figure out on your own. It's much more fun this way. All right, so where is the energy in the initial situation?
Car
In car A, absolutely. What kind of energy?
Kinetic.
Kinetic, yeah, totally, right? So normally I do like kinetic is blue, but I'm gonna switch the coloring, and I'm gonna color them like this. So let's make car A blue. Is that cool? I'll make car A red. Car B is red. Okay, how's that? Is that cool? So where's all our energy to begin with?
Car.
Car
It's in car A, right? It's all kinetic?
A, yeah.
All right. How's that? Is that good? And what about our final situation?
Car,
Yeah, so car A comes to a stop, so what do we end up with over here?
move from car.
Is it all there? So this is a great question. Is all the energy transferred?
Yeah.
Maybe. How would we know? Okay, how would we know? So, in order to calculate the kinetic energy, what do you need to know? It's 1/2 mv squared, correct? Right? So I know that each of these cars has a mass of 1/2 kilogram. So m is equal to 0.5 kilograms. And when I push this, it's about 60 centimeters per second. So I would say that the V is equal to 0.6 meters per second. Is that, I just want to make sure that's reasonable. Does that seem okay to you? Right? 60 centimeters is about this, and so the car is moving in a 1 Mississippi. What? This is actually always a question in my head. Like, when you guys count, like especially when you're little kids, you use like 1/1000, or do you like 1 Mississippi?
I've seen
What do you guys do?
One.
Just say one.
Just say one, 1, 2, 3. No, you need to say something after so you can get a whole second in there. You're kind of like my 3-year-old. I'm like, here, count to 10. Right? I go, what it'll take me about 10 seconds. She goes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not 10 seconds. That's like 1 second.
I say one.
You say what?
I did. I just say one.
Thousands or Mississippis?
Neither.
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 Oh my gosh, I'm freaking out. All right, so here we go. What's the mass of car 2?
Not the same.
Yep, 1/2 kilogram. What's its speed?
0.
So then what's happening over here, right? Natalie made an observation. She's like, look, this car stops. And then what do you guys tell me about this second car here?
That's 0.2.
It's move off at the same speed as the other one, right? So if I go to calculate this, the mass is 0.5, the speed is 0.6, don't forget to square it. I'll do it in my head real fast. Jacob can verify on your calculator. 0.6 squared is 0.36, half of that is 0.18, and half of that is 0.09. Is that true?
Yep.
All right. And what is the energy of the red car here? What's the energy of the red car? Bueller, what's the energy of the red car? Initially. It's 0 because it's now moving, right? So what is the total energy in the system then? It's 0.09. Because inside the system is card A and card B. So the kinetic energy of card A is 0.09. This one's 0. Total energy, 0.9. 0.09. Does that sound good? That sounds okay. What about over here? What's the energy of card A here? And what about card B? Now, I know that because it's the same mass and the same speed. So I like what, Evan, I like what you got going on here. He says, look, in this collision, all the energy is transferred over. Does that seem to be true? That looks fantastic to me. You guys okay with that? I think it looks, yeah.
Well, I have a question. If one car is heavier than the other, will like the mass still not matter?
That is a great question. So his question is like, look, what happens if, and I have this bar here. So this is a half a kilogram bar. This is a half a kilogram car. Do you see this one keeps moving? That's not a coincidence. Watch it again. Do you see this one keeps moving? It does, right? Is all the energy, well, I should say not all transferred this time because this one still had some energy. So does the amount of energy that this one loses go with the amount of energy that this one gains? That's a great question. I don't really know. Do you think that's something we should explore a little further? I do. I mean, I think that's the actual question that we want to answer moving forward is, what is the role of energy in this? So far, so good? All right, let's do a different, so this is called, it doesn't matter what it's called, but this is an elastic equation where the two objects bounce off one another. Okay? The two objects bounce off one another. So you'll notice this is this time, well, I'll do it in my magnet so you can see. Oh my God. So see, it repels this one. Did you see that? Now I'm going to turn it around. Watch what happens to this one. It attracts this one. So if it repels this but attracts this, what does that mean for these two here? They're going to attract each other, right? So watch what happens if we put them close enough. Did you see that? Cool. So we're going to do something exactly the same, only different this time. I'm going to send this one in. So, did it hit and stick? What do you notice about the speed of the two cars moving together versus the speed of the original car. Check with your neighbor. See if your neighbor noticed the same thing you did. Okay? All right. How does the speed of the two cars moving together compare to the speed of the original car? All right. Check your neighbor. See if your neighbor has an idea. All right, you ready? This is where your intuitive sense of the world has to come into play, and I'm very excited for this moment. Okay? How do you think the speed of the two cars after the collision compares to the speed of the original car before the collision? What do you think? Go ahead.
I feel like it slows down because you're kind of like combining the masses together in one with the same speed.
Okay? He said definitely slower. He said slower. Anyone else agree with slower? Did it look slower?
Yeah.
Now, if you had to guess, how many times slower? She said 2 times slower. She said half the original speed. Anybody else want to get on board with 2 times slower, half the original speed? Does that seem reasonable? Okay. I actually think it's very reasonable. Because you're doubling the mass, does it make sense you would have half the speed?
Yeah.
Okay? And I will tell you, if I put the motion sensors up here, this would be honestly the exact thing that we would see. And we're going to see this later on. So we end up with half the speed. So let's look at it. Okay? So let's look at it up here. If I write this out again, initial kinetic energy of the blue is, ooh, what was that? 1/2 mv squared, 1/2 of 0.5 times 0.6 squared, 0.09 joules. Let's do the red one. All right, ready? Now, we can do a couple things here. We can treat them as one, or we could treat them individually. It doesn't matter to me. Let's treat them as one. It'll be more interesting this way. So let's say that they're now one object. Okay? So what's the mass of my new object? Oh, it's 1. Because 1/2 and 1/2 is 1 kilogram. And what did we kind of intuit the speed to be then? And I like this intuitive sense about like, oh, it's twice as massive, therefore it's half the speed. One went up by 2, the other goes down by 2. That's a really good sense of the world. Okay, that's a really good sense of how the world works. All right, so let's put this in here. So my kinetic energy over here. So 0.09. Okay. So let's go ahead and calculate the kinetic energy of this boy over here. What do you guys think it's going to be? What do you think the kinetic energy of that boy is going to be? So 1/2 the mass, which is 1, times the speed, which is 0.3. So 0.3 squared is 0.09. Half of 0.09 is 0.045. Uh-oh.
It's just half over here.
It is half. But that's weird. Where's the other half? Yeah, so this is great because listen to this. Did you hear it hit? Didn't we decide earlier, a couple weeks ago, that if you collide two things together, thermal energy is generated? Remember the paper and the balls and the burning? Remember all that?
Yeah.
So are we getting some? Right? So some energy is transferred during this collision, but some energy is also lost. Is that weird? All right, so this is a really good start. We're going to pick this up tomorrow a little bit.